Science Operations with Virtual Globes by Shipley, Cantrell, and Peterlin.
Okay, thank you for this opportunity to address you on behalf of my co-authors, our collaborators, our partners, our data suppliers. We're going to see if we can do something more with Google Earth rather than just look at the data. So I try this. Here's our problem. Here's a great visualization of CloudSat data provided by NASA. And when we click on that, we click on the Google Earth. So we click on the Earth, but not on the data. This data is a little bit strange. It's a COLLADA model. Many of you are familiar with it. And it's a set of triangles. It's the same kind of file that's used in the Sony PlayStation. Based on COLLADA, an image is draped over that or stretched across it, and we would like to understand what's going on in that triangle. So, what we'll do first is go and, we're going to use the application programmer interface this time. The documentation is at that link. This demonstration will use Google Earth 5, but it's also available for the Web API. This has been supported by NASA SBIR funding. And we're pleased to have this opportunity to give our first presentation. So no one's seen this before. And you'll be seeing a prototype in action, which we call version 21Q. Lots of versions. First time never works. So first we need to go get data. This is courtesy of NASA through the GIScience project. There's a lot of clicks to do. And we come up with this particular image of a CloudSat data. I like this particular data set. It's Hurricane Dolly in July 23rd, 2008 over the Gulf of Mexico. Very nice set of data. We will then bring up our transparent interface. Now, this transparent interface is going to access Google Earth through the COM API. And I'm going to walk you through a couple of the functions. It looks like a very kludgy interface, but it does actually exercise each of the functions of the API. And let's see, so up here we're seeing the lat and the lon and the height of where we're going to click. And down here I'm going to be either working with Google Earth or with an object, and we're going to call this an object. So the data, which is distributed in space and not on the Earth, is now what we call a focus object. Now I can go up here and get the point of view, which is a function in the API, which gives me the center point of the render window, which is this. And you'll see here's the latitude, longitude, and the height. It's at the surface. I can also then set the point of view. And I'm going to set the tilt to 80 degrees, for example. So instead of using a manual control, I'm now, through the API, everybody who does APIs knows this, we can control Google Earth looking at the tilt or the azimuth, and we can run programs that will do that and do things similar to what the tours do. Okay, so now if I'm looking at the data in a close-up here, and I click this point, and over here I'm in Google Earth, I get the latitude, longitude, and the altitude of a point near the coastline, and this is Google Earth 5, so I'm looking slightly underwater. If I run over here and load the focus object, this particular one, I examine the structure of the COLLADA model that NASA used to create this data. And I think I have to set the object here, and then when I click on this point, I am now through this transparent interface clicking on the data and not on Google Earth. So I'm clicking and getting the information at this particular point in this triangle, and I get information here for diagnostic purposes. I'm in triangle 321. I'm getting the coordinates of the image. I'm looking into the data. I get the color of the pixel that's at that location. I can do more, so just hold on. But this is a fundamental GIScience type of operation. Can I click on the data and look and examine it its structure? Now, WxAnalyst is the name of it, and where did I come up with WxAnalyst? It's derived from syzygy, which is an alignment of astronomical bodies. It's pronounced WxAnalyst, and we've trademarked it. And it's what it means is the alignment of winds in a tornado. Oh, we have sound too. And here in a supercell tornado, we have multiple suction vortices with winds. We have rotational velocity going around the center, and the translational velocity. They all add up to create a lot of wind. Now, getting into the structure of this data, CloudSat, by the way, is a radar operated on the A train, on Aqua EOS satellite. It is looking down. It's a lot like TRMM, but in a higher orbit inclination. And this data has a lot of models put together with images draped over them. We have found something new, and I'll release it now to you guys to think about. An external command that if we click on this point, can we interact with another program? Now, if you read this particular book by Remy Arnault, and you look in detail, you'll find that there is an ability in COLLADA, it's in the spec, to set a statement called extra. Extra is my interface, it's my language, I can throw it into the COLLADA file, it doesn't bother Google Earth one bit. And my interface, when reading the COLLADA model, we can tell what we want to do. So I've got statements like I can give a name, I can give an address, I can pass coordinates that I clicked on to an external program. Here's an external program. I can set the units in case the data is distorted, so I can adjust altitude in this case. Here's one, load data. Now, an author can now sit, and let's do external command, and we can load data that is correlated by the author with this particular segment here, this COLLADA model. This happens to be NexRad data from Brownsville, Texas, KBRO, at the same time, at the same location, looking in the same position. If we could take a little tour of this. The NexRad data is 4 levels. They're conical scans. It takes about 30 seconds to go around. There's a whole hour of data here. And you can see there's an intersection with this overflight, which comes by here in a few minutes. And we're going to look at, in detail, at the intersection of these two data sets without leaving Google Earth. So here's an examination of these two COLLADA models. This is the 1.5 degree beam elevation for NexRad. There's a lot of triangles here, a lot of images draped over that. It's actually one image draped over that at the same time as the overpass. And by looking in detail at the intersection here, you can see that we have a curved line which represents where the radar has intersected the satellite overpass. This is our transparent interface now reduced to get out of the way, and we can examine the data from either this data set, the NexRad one, or the CloudSat one. And why don't we see if we can do an intersection? So this is where GIScience becomes interesting. Here's an automated way to read both COLLADA files, find out where they intersect, and gather the points of the intersection along here. You've already seen that we can go into the files, get the image data, and pull it back out. With the external or the extra command, type external, we can also use author-determined links to go to an FTP or HTTP or a source where you have other data that you might want. You might want to have this data in its original format, and we can query it through the extra statement. So this is really kind of interesting capability. If we come back to this area, I'll show you a little bit of physics here, that this is the 1.5 degree elevation surface. Here is CloudSat looking down. Red is very high reflectivity, and you see there's a hole here. But the NexRad at 0.5 degree elevation shows that there's precipitation at this location. So what's happening here is there's the attenuation of the beam is so great, of the radar beam, that we've run out of signal, and we have a hole So we can detect this now by doing simultaneous data on data and correlate them, and without leaving Google Earth. Okay, sort of jumped ahead. This is the same area, but we're going to take our focus object and throw it down. See, can I go back? There we are. This is under the water, and we're going to drape on the water here the cross-section of temperature below this section from a model. And it's this one where we can go further down by a trick that Declan showed me last night. So thank you, Declan. And we can, by this demonstration, I can click on the nose of this flying cow down here, and we can get the location below the surface of where our COLLADA objects are. So we can now also extend this kind of operation to below the surface. Here's another look, the same data here, but now we're going to go with Naval Research Lab and add in this IAS NFS data for temperature and current at 50 meters. This is not a ground overlay set down at -50 because that does not have really great results. This is the image draped on a COLLADA model, which is a set of triangles, and you can see that it does the intersection with the coastline incredibly well. So we have put this data in position where it is. Here's another set from NRL of looking at their model forecast for bathymetry, and again using a Duport technique, cross-sections Duport. We're going to extend them up. The advantage of this is that we get good magnification of the scale and the vertical, because if we put this to true scale in the ocean, they're so flat that we can hardly see anything. This will also animate. So these are curved COLLADA surfaces, cross-sections, running through, they're set to go along sea level. Now here's my wish list. I have two wishes. One is that I would like to have a tool that works like iTunes does. I run iTunes, put it on my system, it scans my system, organizes my music, so why can't I do that with spatial data? Turns out I can, and here's something that does that. It's called My Earth, a product by co-author Simon Cantrell. Now what this will do, it pre-scans my file system, finds HDF5s, NetCDF, shape files, KMLs, KMZs, finds out where it is, creates browse metadata in Google Earth, and then allows me to search on that using these spatial search options for time and for space. Here's the same data you saw earlier where the system has browsed and created browse images for all that data. So I'm in a position now where I can go to somebody's computer, look at what data they have spatially, run through here and click on this data, examine the structure of their data, and if there's extra statements in here, I can map to other data sources. This is opening the door for some new things. My wish list number 2 is to Khronos.org. These COLLADA surfaces are straight lines, triangles, images draped and stretched over these polygons in very linear ways. You can see the network here of triangles used to drape this image at 50-meter depth for currents and temperature below the ocean surface. So what I would like is an extension to this that would use arcs and spherical surfaces. So circular arcs and spherical surfaces would allow me to reduce, or allow us to reduce the size of these browse images. Now, getting a little more complicated, we can use the tool, here's the interface down here, to examine NetCDF data. This happens to be an MM5 model in a project done for the Navy by Simpson Weather Associates, and they're flying an airborne LiDAR, Doppler LiDAR, and these are wind profiles we put together. You can see the model points at the bottom. Using the tool, we examine the model structure at a specific point. We can extract or create from it a wind profile, which you see here, and then calculate wind trajectories and do a computation of the differences between the model and the measurements on the fly without leaving Google Earth in the airplane as we're flying, which is phenomenal. All of this has been also done with the Web API. So we've, as part of the project, we duplicated the effort in the Web API to prove to ourselves that it could be done. And as a parting comments, I've shown you that we can analyze and edit focus objects without leaving Google Earth. Google is moving, by their own admission, to the Web API, and we're hearing that the COM API might not be supported in Windows on next version of Google, which would be 6 of Google Earth. But that's okay, because we can always use WorldWin. And we would just develop a COM API as open source on WorldWin, and then all these tools we develop should work as is. Here are my collaborators, extensive number of people, and Java Tonks here, who sits at my computer and wonders, when am I going to be finished? Thank you. I think I'm finished. Thanks a lot.
Thank you. Do we have a quick question? Yes, Mano.
So given that the COM API is likely to go away, why wouldn't you use the Khronos plugin instead of, say, WorldWin?
The which plugin?
The Google or Khronos plugin?
Oh, we are using that. That was slide number 30. That we have done the Web API using the plugin. It works with the plugin. And we're just trying to tell all the government agencies and everybody we know that they should pressure Google not to remove the COM API. And we're working really hard at that. And the question was, why don't we use the Web API? The comment is we can embed the Web API into the desktop application. Yes, we understand. But we have to be connected to the internet to do that. There's a number of reasons to stay with the COM API. For instance, running on an airplane in the middle of the Pacific in a tropical cyclone, for example. Thank you.
Okay, thank you.